Hey everybody, and welcome back to Calc 3 Online. So the plan for today is just basically in 30 minutes I'm going to try to go through as many problems related to some of the first semester stuff as I possibly can. And there's a lot of really important stuff, so I'm just going to jump into it. And all of these problems are ones that I really want to make sure you know, because they're all kind of what I view as like some of the most important things that we've studied so far. So first one is just a limit problem, and I want you to either, I'll give you limits like this, and I'll say either like find whether the limit exists or doesn't exist, and if it exists, like what is the value. And a lot of these ones, right, you're basically just like, if you look at, kind of imagine like this is like a top view of the function. You might like come into so we're talking about the origin, and a lot of times we came in and like checked the value as we come in along like an axis, like maybe the X or Y axis, but you could also like come in along like a quadratic like that or something, or you could even come into like the origin on some sort of like cubic, so maybe you're coming in on some sort of cubic, and so, the idea is like no matter what path you would come into the point at, the value of this surface must be the same, right? And so if we can find two that are different, then we've shown that the limit doesn't exist. So, one common trick is to just do like coming in on an axis. So basically here I'm coming in on the x-axis. Then, all the y stuff simplifies out. So, I have a y squared on top, so it's going to kill the numerator, and then I'll just have x to the fourth on the bottom. And, we know that limit goes to 0, right? As x goes to 0. So, that's nice and kind of easy to see. And then, if you notice, okay, these are the same value. So if I came in on y equals x, I could combine these into one term, and then I should be able to simplify it with this. And that's like a common trick to help me do some of these limit problems. So if I come in on basically y equals x to the origin, the surface I have would simplify to this. And then that would simplify even more to, so you'll have like 2x to the fourths on the bottom. And then you can, simplify that with x squared. So you basically would get sine squared x over 2x squared. And I'm going to just simplify this even a little bit more and get this, right? So here, I've just pulled a half out, and then sine x over x, squared is what sine squared x over x squared is. And this is like a classic, L'Hopital's problem. So if we do L'Hopital's right here, we would basically get that this thing goes to 1, right? And so then this whole limit would go to 1/2, which is 1/2 times 1 squared. And then we've come in to the point on two different paths. Specifically, we came in on y equals x and the x-axis. And since 0 doesn't equal 1/2, we know that basically the limit doesn't not exist. So it means that like these are two different z values, right, that we're approaching on this surface as we come in on the x-axis and y equals x. All right. Another very important problem is like optimization stuff. And the kind of harder version of optimization, I don't even know if it's per se harder, but definitely more time consuming, are these absolute max and min problems. And so I wanted to do one of these. So I always start off and like sketch the region. Okay, so we have the region is defined by x greater than 0, y greater than 0, and then x plus y is less than or equal to 2. So if you graph this, right, you'll be up at 2, and then it's just, actually I'm going to just do that. So it goes from here to here, and then that means we're getting this kind of triangular region, all right? And I'm going to just sort of label some sides here. So we'll call this line 1, and this is going to be line 2, and then this is going to be line 3. And so the overall like broad strokes here is we need to first check max and min stuff on the inside of it. So any like possible local max or min could still be the absolute max or min. And then we also need to check the function on the boundary lines, line 1, 2, and 3, and optimize it on there and see, like compare all those basically. So let's just start with, local max and min. All right, so we'll start off, we're going to basically find the critical point. So the partial with respect to x is 3x squared minus y minus 1. Partial with respect to y is negative x plus 2y. And in order to be a critical point, basically both of these need to be set equal to 0 and solved. So you can see from like the f with respect to y that basically x is 2y. And so if you sub that into the first one, right, basically just solving the system here with substitution, you're going to get 12y squared minus y minus 1 basically needs to be equal to 0. And this thing has roots of a third and negative a quarter. And I guess similarly now, the corresponding x for a third would be 2/3, and I just do it off of x equals 2y. And then for the negative quarter, it's negative a half, right? 2 times negative a quarter. And then you can go and like plug these things in. So if you do f of 2/3, 1/3, you get negative 13/27. And if you do f of, negative 1/2, negative 1/4, you will get 5/16. Okay. So basically right now we have 2 contenders for the absolute max and min. And these could honestly be them, right? This could be the absolute min and this could be the absolute max. Those 2 points are like the critical points inside, like the shaded area inside, right? But, if we're thinking like extreme value theorem stuff, we know that this surface could attain its maximum or minimum on the boundary, right? It could from, one of these points in the middle, it could just grow and grow and grow or something, and be an absolute max. It could just be higher over here. It's not necessarily a critical point because the function doesn't flatten out there, but because of the cutoff with the boundary, we might have the highest value still. So now we just go and basically start evaluating on the different boundaries. Okay, so we'll do line 1 first. So line 1 is the green one. And here we have that y equals 0. So basically we get the function to just look like x cubed minus x, which we can factor an x out. Get x squared minus 1. But you could even, if you want to factor this one more time, right? So you get that. And honestly, the way I think about this thing, we have a root at 0, negative 1, 0, and 1. And, basically it looks like that. It's that kind of cubic. It's a positive x cubed, so it's going up. And so, this was at 1 and 2 is out there. And so we can see that at 2, it's going to have its highest value. So it's going to have, we'll just keep in green here. So at x equals 2, we're going to have this function giving us 6. And the minimum would be in between these two. So f of 1/2 is basically going to be, wait, my bad. I don't think it's actually that symmetric. So really what we should do is we need to figure out, so we should take the derivative of this function to find this critical point. So we're going to optimize and we're going to figure out that minimum right there, right? And so the derivative of x cubed minus x with respect to x is 3x squared minus 1. And I would just use like quadratic formula. And, you're like setting this equal to 0. And if you do that, you're going to get that x is plus or minus square root of 12 over 6. And so this is the minus square root of 12 over 6 over here, but we want this one because 0 to 2 is the only region I'm concerned with, right? And so then the other contender here is square root of 12 over 6, if you plug that in. And if you plug that in, you get the minimum of negative 0.3849. Okay, so that's line 1. And then, so line 2, okay, basically this line 2, you could just set y equal to 2 minus x, because it's just the, that diagonal line. And if you go and plug in, y as 2 minus x, you can simplify this thing to just a function of x cubed plus 2x squared minus 7x plus 4. All right. And so for this one, I would probably do the same kind of thing. If you take the derivative of that guy, then the derivative of x cubed plus 2x squared minus 7x plus 4. I would just do that to figure out any critical points. So you get 3x squared plus 4x minus 7. And the roots of this thing, if you set it equals 0, are 1 and negative 7/3. And so this is saying that, this one is not useful because it's not between 0 and 2, right? But the 1 is, so we'll have to evaluate it at that, okay? And so if you do f of 1 for this function of x here, okay, you actually get 0, which is nice. And then if you look at the boundary, so at 0 and at 2, so f of 0, right, could be a max or a min, but you can see that if you plug in 0 here, you get 4. And if you plug in 2, actually if you do that one out, okay, if you do f of 2 here, you'll actually notice that you get a higher value. Specifically, you get 6 again. Which really shouldn't be surprising because we checked that point already on the green line, so we really don't need to check it again. But this gives me, kind of 2 more contenders. So, so far now, I didn't circle these ones, but we had f of 2 equals 6, f of root 12 over 6 equals that negative 0.3849 thing. And then we had an f of 1 equals 0. And an f of 2 equals 6. And so those are the, max min values on line 2. These are the max min values on line 1. And now I need to do line 3. And I'm out of room, so I'm going to erase all this stuff and start over just actually erase the green stuff, and then I'll kind of sum it all up here. So you can always reverse the video and watch the rest of this. But I'm going to erase all of this part. All right. And that too. So we'll do orange. Nope, we're going to do purple because that's the line. So line 3, this last one's not too bad. So here we have that x equals 0. So basically it simplifies this thing to literally just, so f of 0y would look like just literally y squared, right? And y squared, so between 0 and 2, this one is a very nice one for us to think about, like this, right? The easiest of them all. And we know that it's going to have its minimum at 0 and its maximum over at 2. And so if you do f of 0, 0, you get 0, which which makes sense. And then f of, what's the other one there? 0, 2. And f of 0, 2 would give you 4, right? Which also makes sense, which we found before. So we have all the points now, and now you just got to see what's the biggest and what's the smallest. And if you go back through and look at this thing, 6 was the biggest we ever got, so that's my absolute max, okay? And we had 2 negative numbers. One was I erased. It was like negative 0.3 something. And this thing is like negative 0.4 something. So that one is smaller. So that is actually my absolute min. So that's it. So those are the 2 biggest values you get on this surface, considering this boundary. And one of them happened to be an interior point, right? So 2/3, 1/3, somewhere about there. And the other one happened to be over in this corner. They're actually like, So the broad strokes, again, just you have to do the interior critical points. And then you have to go through on all the boundaries and simplify this equation to, based on the constraint function on the side. Like for line 3, it was just x equals 0. And then you optimize the constraint on there. Whew. All right. So now for something much shorter. Another really just important thing from this course is writing the equation of planes in like different forms using things like here I'm just asking for vector and standard form. So if you have 3 points, you can do this. So basically the idea is like if you have some sort of plane, you have like point P, Q, and R, right? You can basically get direction vectors like P to Q, P to R, and you can pop those in to like the correct spots, and you will have the equation of a plane. And so this is my vector form, I guess is what I'm talking about first. So we're gonna have XYZ, and then we have to have like a point here, which I can just do as 1, 1, negative 2, point P. And then you have to have a direction vector that you're going to scale, and then add to that another direction vector that you're going to scale. And so the idea is like you can create this plane if you start at P, scale this direction vector, and add to it this scaled direction vector. And that really would just fully describe the important components of this plane, okay? So then you just got to do P to Q and, P to R. It doesn't really actually matter, per se, which ones you do. So PQ, just going to do Q minus P. And so if I do Q minus P, I'll get negative 1, 1, and then negative, I'll get 3. And then we'll do P to, we'll do a different color. We'll do red. So P to R, my initials. We're going to get -1 minus 1 is -2. -1 minus 1 is also -2 still. And then 0 minus -2 is 2. And so then we can just go ahead and put those in. And that is the vector form. So this one is very popular in like linear algebra, a lot of computer science. The way this works again is it's like you have a point, and then you're adding to that point a scaled direction vector. And again, from there, you add another scaled direction vector. And basically, if you add that up and you let these scalars be different things, you can get anything in this plane. And so that describes the plane. All right. So probably for standard form, the easiest way to do this is we're just going to take, so you could create a normal vector just by doing a cross product, right? And actually, let me make that a little bit better here. So make it over here. So I'm basically going to make a vector that's perpendicular to, this one back here, and also this one up here. And that's just, going to give me my normal vector, which then if you just know the right structure of it, you can get the standard form. So we're going to do cross product ijk, take a determinant. We're going to pop in my PQ vector, and then my PR vector. And then if you do that out, you get 8, -8, 4. All right, and then the correct form I'm talking about is basically you put 8 in there, and then do like x minus a point. So I'm just going to use point P, x, like minus the x component of the point. And then we'll do -8, and then y minus the y component of point P is what I'm using, but you could use any point. And then we'll have 4, and then z, plus 2. And you could, and you probably should, simplify this out, but I'm not going to this second. So that is a unsimplified standard form. And then this is my my vector. Form. All right. So another thing that goes back to around that time are these problems related to the distance between like parallel planes, and they just use tons of good. So the plan with these kind of problems is to just, so I would always draw them first, okay? So we have like this plane, and then we got some other plane down here that's parallel. Those are horribly drawn. I'm actually going to try to do that a little better. And the idea is like you have, you can find some point in this one and a point in this one, and you can create that vector, right? And then you could find like a normal vector that comes out of, they're either plane, really. And then the idea is like we can take the vector in yellow there that we created and project it over onto the normal. And what that's going to do for me is it's going to scale that normal up. And if I take the magnitude of that red vector, then that thing is really going to represent the true distance because it's the vertical like measurement between those planes. And it's really important that you know, like, this part 2, there is technically like a formula that just does it for you, but I've never really wanted you to use that. I want to see this kind of work because it really utilizes some important like Calc 3 vector computations. So I'm going to start and just get a point in each plane here. So, one point that's kind of easy to see here, and the first one is -3, 0, 0. Because you can just like get 9 and then plus nothing is 9. And then likewise over here, you could do 3, not negative 3, and then just 0, 0. And 6 times 3 is 18, and then plus nothing. And so the yellow vector that is going to go between the planes on like a diagonal could be let's see, so it could be negative 3 minus 3, so negative 6, and then 0, 0. All right. Actually, I don't like negatives, so I'm going to do 3 minus negative 3, and I'm going to make it positive. And then the normal is, you can really pick either of these. It doesn't matter. I'm just going to pick the smaller one because the numbers are nicer. All right. And then the distance between these things is truly just the magnitude of the projection of v onto that normal, and it'll scale that normal up appropriately. And so we're going to do, v dot n here over n dot n times n. That's the magnitude of that thing will be my answer. And v dot n is negative 18. And then n dot n is 9 plus 4 plus 1. And then we got negative 3, 2, 1 here. And if you compute the magnitude of that thing, right, just the sum of the square roots or the squares of every term, you should get something that's like about 4.8. So the idea is, of course, more important. I really want to make sure you know what you're doing. I don't want you to just memorize a formula to do something like this. All right, another just really important thing are directional derivatives. And I just want to do another one of these. So I want to calculate the directional derivative of f at the point 1, negative 2, 3. And one of the things that you got to always be careful of is that the direction that you're going needs to be a unit vector. If it's not, basically the idea is if it's longer, it's going to kind of give you more slope. I'll put that in quotes. And if it's less than 1, it'll give you kind of less slope. So we got to make sure that we normalize v. So we're going to go ahead and do that. All right, and we would get that. So that is what I'm going to take as my unit vector. And then I got to basically dot my gradient of f. So let's do it like this. So gradient of f with u. And if I do it evaluate the gradient at the point, then we'll have the amount of slope change in that direction. So my gradient is this. All right, and then I need the gradient at the point 1, negative 2, 3. So if I go and plug that in, I will get that. And then I just need to go ahead and do, this dot product. So if I do 23, negative 16, 17, dotted with negative a third, 2/3, 2/3, I would get negative 7. And that is the directional derivative of f at that point. So basically that tells me that, if I look at this direction, if I graph this weird looking thing out, it's some 4-dimensional object, right? But it's telling me that in that direction, this thing is basically decreasing, okay? And it's decreasing at that rate in the 4th dimension.